We were talking about Mobius transformations. Which are mappings of the kind like this. And what I was in the middle of showing you was that Mobius transforms map lines to circles or lines. Okay, and we showed that M can be thought of, or can be written as M of Z is equal to L2 L1 of Z, where L1 and L2 are affine mappings. Right, i.e. Affine. I want to write specifically what L is because it's a specific form. Affine means we have Z goes to, say, AZ plus B, right? That's an affine mapping. So the fact that affine mappings send lines to lines, circles to circles is trivial. So the real thing that has to be checked is that this thing, the inversion mapping, actually does that. Okay. So Mobius transforms space with an affine mapping, then it inverts it, then it transfers it back. Cool. Okay. So we were somewhat into this. Let me call some part of this. I think we showed was that if we have a circle that goes through 0, then that is mapped to a line. So first, let's observe how we can write a line in the complex plane, or the equation of a line. So look at this. So if we have Z like this, then typically we write a line something like this. Say AX B is equal to C. That's how we write a line, right? That's the equation of a line. Yeah, that's a line which goes orthogonal to the vector A comma B, right? And the C here dictates where in space it actually is. If C was 0, then it would be the line orthogonal to AB going through 0. Yeah, you're all happy with that, right? Yeah, thumbs up if you are. Yeah, cool. All right. So if we wanted to write this in complex coordinates, well, what do we know? We know that we can write X like this. So we can write this as Z plus Z bar over 2, and then B as the Y. We can write this as Z minus Z bar over 2I and C, right? Because if we do that, then we kill the X, and yeah. So this is another way to write this thing like this. And then if we solve for Z and Z bar, then we get the following equation. We're going to have that Z over 2, and we're going to have an A, and we're going to have a B. So we're going to have A plus B, right? And then for the Z bar, we're going to have Z bar, and let's put it over 2. And then we're going to have A, and now we're going to have minus B over I. And 1 over I is just minus I, so that's the same as, let's write it like this, A plus B over 2, and then Z bar of A. And this guy becomes now just plus IB, right? Over 2. And then we see that this guy is this guy complex conjugate, right? So if we define A to be equal to A minus IB over 2, then A complex conjugate is A plus IB over 2, right? So then we can write this thing as Z A plus Z bar a complex conjugate, yeah? Which means that we can write our equation like this. The equation of a line can be written like this for some complex number A itself, yeah? Cool. So we have this nice way to represent the line, which we will use later. Okay, so let's jump back into trying to see what happens to lines or circles as we transform it with this mapping 1 over z. So we were somewhat through the case when we had a circle. So if we have a circle and it's given by the set of z such that mod z minus a squared is equal to r squared, right? That's the general equation of the circle. So we know that if mod a equals mod r, then it's going through 0, and then it's actually transformed into a line. That's what we've seen before. A line, right? And so we're going to have to consider, or we're going to consider the case when this is not actually true, to see what is more general. So we consider mod A is not equal to R itself. So the circle is not going through 0, right? So this is 0, this is A, and we no longer have the radius is going through 0. Something else is happening. Okay, so how are we going to do this? Well, we just expand out what the circle means exactly as we did before. So the equation of the circle can be written as z minus a complex conjugate, z minus a equals r squared, and then we expand that out. We're going to have mod z squared, we're going to have a minus this thing times this thing, and we're going to have a minus a times z bar, which is this guy times this guy, and then we're going to have plus mod a squared, and that's equal to r squared. Now we put the a squared on the other side, so we have this thing, and we're going to have r squared minus a squared like this, right? So last time this thing was 0, so we got something simplification, which isn't going to happen here. So this is not 0, and we are going to divide by mod z squared on both sides. So we're going to have 1 minus a. This is wrong, of course. This is like this, and this is like this. Yeah, we're dividing through by mod z squared. So we're going to simplify this, because what is mod z squared? It is z times mod z. Start again. It's z times z conjugate. So we're going to cancel the z's here. We're going to cancel the z conjugates here, and what we have is therefore 1 minus a over z conjugate minus a over z is equal to this thing, right? Now, this thing we write as 1 a bar, and this is the same as having I of z complex conjugate, right? Because I is just 1 over z, right? And then this is the same as minus a I of z, and then this thing here is r squared minus a squared times I of z squared. Yeah? Cool. So, so what I said previously, I should have not said at that point. I'm going to say it now. If r squared minus a squared is equal to 0, then what we have here is exactly the equation of a line for the image of z under I. Yeah? So the image of z under I is, I'll start again. the image of the circle under I is exactly forming a line from this equation. That's where we were before. Yeah? But from exactly the same thing, we can see that we can mess around with this and actually get something like a circle, because this was the general equation of the circle, and you can see it's looking a lot like this already, right? It's looking a lot like this already. So what are we going to do? We are going to divide by r squared minus a squared throughout everything. So then this implies that 1 over r squared minus a squared minus a r squared minus a squared, this thing, and minus a over r squared minus a squared. This guy, oops, put it up. Right, and then this thing on the right-hand side is just I of z squared, right? So it's looking more and more like this equation here, right? So when I erase the board, maybe see if I can put everything on the same board. Maybe that's easier. Let's give that a go. Okay, let's see if I can do this on one board. Now, every time I try and do it on one board, it just looks terrible. All right, we're just going to erase. So what we had was, we had 1 over r squared minus a squared minus a over r squared minus a squared times I of z, and then minus a bar over r squared minus a squared times I of z bar, right? And then this is equal to I of z squared. This is where we were, right? Cool. And we want to turn this into something like the equation of a circle, because that's what we expect it to be. So we're going to put these guys on the other side, right? So then we're going to have I of z mod squared plus a over r squared minus a squared, z plus a bar of r squared minus a squared, I of z bar, right? And put these on the other side, and then this will be equal to 1 over r squared minus a squared. Yeah, and then let's kind of complete the square to get this expression. So what will do that for us? So what if we do this? What if we have I of z, and let's do minus, well, plus, I was going to do minus, but let's just do plus a over r squared. So if we multiply that out, is that going to work? Let's try this. So when I'm running a squared, I mean mod a squared throughout. So. Specify that. Okay, so let's see if that does the right thing. So when we multiply this and this, then we don't get what we want. So I need to have this and then like this, right? So then if I multiply these guys, I get this and I get this. So that is what I want. So what I'm going to do is I'm going to do this. Yeah. And then that thing is indeed the same thing as minus mod A squared. Yeah? Cool. So we have this thing is the kind of completing the square that'll give us these terms. So it'll give us this extra term of this thing multiplied by itself, right? So we have this thing, okay? But what we actually need is to recover these guys. Change color. So recover these guys. So we have from that thing that this is actually equal to mod of z plus a bar of r squared minus mod a squared. And then we are going to subtract mod a squared r squared minus mod a squared. Yeah? That thing is equal to that thing. Yeah? And that thing itself is equal to this thing. R squared minus mod a squared. Like this. Yeah? Okay, so we're almost there. So we put the stuff on the other side, so we're going to have and on the other side, we're going to have, let's make the common denominator. So let's write the top as r squared minus mod a squared. And then, plus mod a squared. So that's a nice cancellation over this thing. Like this. Yeah? Which just turns out to be this, r squared over r squared minus mod a squared. And what we've just written down is the equation of a circle, right? It's the equation of a circle, which is centered around minus a conjugate over r squared minus mod a squared, right? And whose radius is given by this thing. Yeah? Okay, let's see if we believe this. Let's see if we believe that this makes sense. So, if, for example, we have a huge circle, right? A huge circle, but a is just some number, right? So suppose a is here, but we take the radius to be huge, right? What would expect this inversion map to do to that circle? Right? Suppose we have a circle which is like going out like this. We'd expect this inversion map to do what to that circle? Send it to a small circle, right? Yeah. It's still going to be a circle, but expect it to be quite a small circle. Yeah? And then let's take a look. So A is of order 1, whatever. It's much, much smaller than R. We're letting R go to infinity. And then this thing on the right-hand side is indeed going to be very small. It's a small radius because we have a power of 4 of R here, the power of 2 of R here. Yeah? And indeed, the center is going down to 0 as well. Yeah? So this is indeed sending this huge circle to some sort of little circle, whatever. Yeah? The bigger circle, bigger radius we take, the smaller radius the inverted circle is going to be sent to. Yeah? Yeah? As we've seen before, if we have a circle whose radius goes through the origin, then this thing turns into a line, right? Which is kind of equivalent to having a circle of radius infinity in this expression here. Yeah. So this thing seems like the right thing, and this has shown that with this inversion map, we are sending a circle either to a line or a circle. Yeah. And just following from the algebra. Okay, so final case to check is when we have a line. So suppose we have a line. And we've now learned that we can think of a line, or we can describe a line as a complex conjugate z plus a z complex conjugate is equal to some constant like this. Yeah, that's what we've learned. Cool. So we have cases to consider. Suppose C is not equal to 0. What would you expect this thing to be? I mean, it's got to be a circle or line, but which would you expect it to be? And what does the inversion map do? Suppose we have a line. So we have a line, right? We act on this with the inversion map, right? So it's got to be, if the theorem is true, it's sent to a circle or line. Which do you expect is most likely, given what we've learned? Right, so the inversion map is going to send 0 to infinity, right? And anything which stays away from 0, then it's not being sent near infinity, right? So this line here is not going to get that big. I mean, the image of this can't possibly get that big because we are always missing 0 by something, yeah? Yeah? So if the image was the line, then the line goes off to infinity, yeah? We can go as close to infinity as we like with the line, yeah? So it would be impossible for the inversion map to send this line to another line, yeah? Because we can see the inversion map is just not getting close enough to 0 to, it has to go through 0 to actually be sent to infinity, yeah? So we'd expect this line, which is the same as when C is not equal to 0, to be sent to a circle, yeah? On the other hand, if it's a line going through 0, then indeed the image will contain infinity, right? So it should be a line as well, yeah? So it's kind of analogous to the case of a circle. If a circle went through 0, then it turned into a line, otherwise it's a circle. If a line goes through 0, then it's a line, otherwise it's a circle. Oh, that's what we expect. That's what we're gonna see. Hopefully that's gonna come out in the algebra. Yeah? Cool. So if C is actually equal to 0, then we just have A bar Z plus A Z bar is equal to 0. Let's divide everything by mod Z squared, right? So then that's the same as A bar over mod Z squared plus this over mod Z squared equals 0. And then we do the same thing as before. And then we have A, and then we're going to have over Z bar plus A over Z is equal to 0, and that's the same as A times the inversion map complex conjugate plus A times the inversion map like this, and what we have is an equation of a line going through 0 again. Yeah? So in that case, it's pretty easy. Yeah? All right, so now suppose it's not equal to 0. So then we have this. And then when we do this, we get this. Yeah? Which gives us this, which gives us this. Like this. Let's divide through by C, right? So let's just rewrite like this. Yeah? And then you can see what's happening. It's the same kind of thing as before. So we put stuff on the other side. Like this. And minus this over this. And plus A over C. Oops, not plus, minus. And that thing is equal to 0. And then we're going to complete the square again to actually get the equation. So what would we expect it to be? Let's try this. Let's do I of Z, and let's try this. A over C like this. If we do this, do we get what we want? We do not, so we're going to do this, and then we're going to do this, like this. And then we get this, this, and we get this, this. Yeah, so this thing gives us the first three terms, but we get this extra term like this. Like this, right? From this times this, right? So this thing is equal to 0. So then we can rewrite this as like this. Cool. All right. And if we've got this right, then as the line gets closer and closer to 0, then this thing should tend closer and closer to a circle with very large radius, right? And indeed, that's true, because getting closer to 0 means C goes to 0, which means our radius does indeed blow up. Yeah. So our radius blows up and our center of our circle blows up as well. So this is indeed doing what we expect it to do. Cool. So that proves the result. So Mobius transforms send circles to circles and lines to circles and lines, where we only get a line as the output if the circle or the line goes through 0. Well, if the inversion, start again. So we've shown that the inversion sends circles and lines to circles and lines, and we only get a line if the circle or line goes through 0. But in the general Mobius case, then the 0 has a role which is taken by a different number, because look, we have m of z equals az plus b over cz plus d, right? So as we mentioned before, the thing that gets sent to infinity is the thing that makes the bottom equal to 0, which would be minus d over c. So minus d over c is R0. So if we have a line or circle that goes through minus d over c, then it's a line, otherwise it's a circle. Yeah? Cool. So that is one of the initial remarkable properties of Mobius transforms.